Okay, so now that we've seen how to calculate E of the cell under standard conditions by looking up the standard reduction potentials, let's take a look now and see how that electromotive force, the EMF, the cell voltage, or the E of the cell, is related to things we've discussed previously, such as the Gibbs free energy, as well as the equilibrium constant K. And we're going to see some pretty important relationships between or among all three of these things. So the first thing that we need to keep in mind here is that the electrical energy that's produced in a galvanic cell is the product of the cell potential and the total electric charge. Okay, so the electric energy in a galvanic or voltaic cell is the product of the cell potential and the total electric charge. And that charge is in the unit of charge, which is coulombs, that passes through the cell. Okay, so we've talked about the fact that the in that galvanic cell, chemical energy is converted to electric energy, right? So that's kind of where we started this whole discussion at the beginning. We said electrochemistry is the relationship or seeing how chemical energy is converted to that electrical energy. So remember now your electric energy, which is, again, the unit of energy is going to have joules, is the product of volts times the charge coulomb, right? We saw this before. We said that the voltage is equal to joules over coulombs. We just rearrange this equation and we get joules equals the voltage times coulombs. Coulombs there is the unit of charge. Voltage is what we've been measuring or calculating previously. So the electric energy, joules, product of coulombs and volts, and the total charge then is the product of the number of electrons that we have in terms of moles times Faraday's constant, which we abbreviate as big F. So Faraday's constant is a constant, doesn't change, it's named after a scientist. And 1 Faraday is the same as 96,500 to 3 sig figs coulombs per mole of electrons. Now, back from our equation up here, we can now do some substitutions. If V equals J over C, then coulombs is the same as joules over volts. So I can substitute J over V for C in this equation, and I end up with 1 Faraday is 96,500 joules per volt, and then that times moles of electrons. So the charge then, well, Faraday's constant, being related or expressed now in terms of joules and volts. So that measured cell potential that we can hook up to a voltmeter, for example, that's the maximum voltage that that particular cell, whatever that cell is, can produce. And that's used to calculate the maximum amount of energy, of electrical energy that can be obtained from whatever that chemical reaction is. And that energy then can be used to do electrical work. So the work, let's say electrical, is simply equal to the maximum, right? That's the maximum work that that we're describing here, and that is equal to negative value of N, the number of moles, times F, Faraday's constant, times E of the cell. Now, the reason why we have this negative sign here is to indicate that the electrical work is done by the system on the surroundings, right? If you remember way back when we talked about thermochemistry back in Gen Chem 1, that's what that negative sign for work actually means. It's being done by the system to the surroundings. Now, in chapter 15, we define, or the thermodynamics chapter, we define the Gibbs energy as the energy available to do work Specifically, then the change in Gibbs free energy, delta G, represents the maximum amount of useful work that can be obtained from that reaction. So delta G then is the same as the maximum amount of work, and W max we just described is this. So what we can say then is that delta G, our Gibbs free energy, is the same as the product of N, number of moles, times Faraday's constant, times E of the cell. Couple things to note about this relationship. Okay, N here, number of moles, that's a positive value. Faraday's constant is also a positive value. And we know that in order for delta G to be a spontaneous process, the sign for delta G needs to be negative for spontaneous process. So then if we think about all these things here on the right side, in order for the product of everything here to be negative, right? We know N is positive, F is positive. It means that E of the cell also must be a positive value, right? And what that then suggests is that in order for a reaction to be spontaneous, E of the cell needs to be positive. For that spontaneous process, which we talked about previously, right? We said that if we calculate E of the cell and it's positive, it's going to happen. Equilibrium is going to lie to the right, for example. And this is the reason why, right? We're making the relationship between delta G and now we're looking at E of the cell. Now, if or for reactions where the reactants and products are in their standard states, we can simply then substitute the little degree sign that tells us the standard conditions, and we end up with our equation down here, right? So delta G standard is the product of the negative value of N, the number of moles. Again, N is the number of moles of electrons. F is Faraday's constant. And then E of the cell is that's the cell potential, and in this case under standard conditions, right? So we've just related delta G, something we saw before, to this new thing now we're looking at in this section, which is E of the cell. Now, the other thing that we know from the equilibrium and from the Gibbs free energy chapter, the thermodynamics chapter, is that delta G naught, the standard Gibbs free energy, is equal to negative RT times the natural log of the equilibrium constant K, right? So we know that from the previous chapter. Well, we just defined delta G standard a slightly different way, but they're both equal to delta G. So what that means, I can take that and substitute it here. So negative NFE cell is the same as negative RT natural log of K, right? If delta G is equal to that and is also equal to RT, I can make them equal to each other. Solving then for E of the cell, so if I were just to isolate E of the cell on one side of this equation, I need to divide then both of the sides by negative NF, divide both sides by negative NF. So these go away, negative sign goes away. I end up now with E of the cell being equal to RT over NF times the natural log of K. All right, so we're just doing a little bit of math on this, nothing too complicated, just some substitutions. So under standard conditions, we know that the temperature here is 25 degrees Celsius, which is 298 Kelvin. We know that N is the number of moles of electrons. R here is the gas constant, 8.314 joules per Kelvin mole. N is the number of moles. F there, Faraday's constant, right? So we know that is now, we can express it in terms of joules. So it's 96,500, and that's joules per volts times moles of electrons. And if we substitute all of these into our expression here, so let's put those in. So we have 8.314 joules per Kelvin mole times T, 298 Kelvin, Kelvin cancels, over N times F, so F is 96,500 joules per volt times moles. And then we have ln of K over here on the right side. So the joules go away, moles go away, and we end up with the unit of 1 over volt, which is the same as volts as the unit. And then we evaluate all of this. We end up with 0.0257 volts. And then we have our N, number of moles underneath of electrons, times the natural log of K, right? And that's E, standard of the cell. We can convert this to, instead of the natural log, convert to log for base 10. And then what we end up with is a slightly more useful equation. We have E of the cell is 0.0592 volts over N, the number of moles of electrons, times the natural log of the equilibrium constant K. So now what we've done is we've related E of the cell to the equilibrium constant K. And this is at 25 degrees, right? These are standard conditions. So if we know any one of the three quantities, delta G, if we know K, or if we know E of the cell, okay, we can calculate any of the other variables just by using any of those equations that we've used or that we've seen previously, right? So they're all related to each other. And we've just gone through and did a really quick derivation of this last equation that we have down here, just by making some equalities, etc. Okay, so let's take a look at a couple examples of how we can use these equations to solve for any of these variables. All right, so here we need to calculate delta G naught and K, so Gibbs free energy, and the equilibrium constant for this system. So we have magnesium reacting with aluminum ion to produce magnesium ion and aluminum. So first thing we need to do is to write out the half reaction. So we have Mg producing Mg 2 plus and 2 electrons. So this is going to be our oxidation. And then the reduction would be the Al 3 plus gaining 3 electrons to produce Al solid, right? That would be our reduction that's happening. And we can see that occurring here. Magnesium becomes Mg2 plus, increase in oxidation number, that's oxidation. Aluminum going from +3 to 0, that's a reduction. Okay, so oxidation here, right, that'll happen at the anode, and then reduction would happen at the cathode. Okay, so for E then of our cell, we can calculate that for E for the cathode. In this case, it is the Al minus aluminum minus E of the anode, which is going to be the magnesium. Okay, we can look these up, look up these values in our tables, and then just substitute them into this equation. So for the reduction potential for aluminum, negative 1.66, for magnesium, negative 2.37. Okay, so E here of the cell. So the cathode there is the aluminum, and aluminum, what did we say was negative 1.66. So negative 1.66 volts. If possible, use your parentheses to make sure you don't lose track of the sign. So minus E of the anode, there is the magnesium, negative 2.37 volts. So this becomes negative 1.66 plus 2.37, and that's going to give me, we're going to get positive 0.71 volts. Okay, and that's E here of the cell. So let's take a look now and see how we can calculate the other things. Because once we have E of the cell, we can calculate delta G and we can calculate K. So according to our reactions above, our equations above, E of the cell here is equal to 0.0592 volts over N times the natural log of K. So if I locate, let's take a look here. We have delta G is also equal to negative N times F times E of the cell. Okay, so we have that other equation that we can use. So let's see, delta G naught is equal to negative N times F times E of the cell. So we just calculated E of the cell is this. F here is a constant, 96,500, and that's joules per volt mole. Okay, and what's N, the number of moles of electron transferred? Well, let's take a look at our reactions that we have up here. Okay, and you can see magnesium loses 2 electrons, aluminum has to gain 3. Obviously, they don't equal each other out. We need the lowest common multiple of 2 and 3, which in this case would be 6. So this would have, we need to multiply this entire thing by 3. We need to multiply this entire thing by 2. So we end up with 3 Mg to give 3 Mg2 plus 6 electrons, and then 2 Al plus 6 electrons to give 2 Al. So we're actually looking at the transfer of 6 electrons. So 6 there is our number of moles. So 6 moles times 96,500 joules per volt mole. And then we have our E of the cell was 0.71 volts. Volts cancel, moles cancel. We end up with joules as our unit. Okay, so we substitute that in there and we end up with, what do we get? Negative 411,000 or negative 411 kilojoules, right? So we just calculated, converted to kilos. We get delta G, right? Makes sense. Delta G being negative tells us it's lies to the right, and then our E of the cell was a positive value, confirms that. Last thing we need is to calculate K, and we can calculate K by using a couple different equations. It doesn't really matter which one you choose as long as you have your correct values in there. So we can, for example, use E of the cell is equal to 0.0592 volts over N times the natural log of K. Okay, if you know what the E of the cell is, it's 0.71 volts is equal to 0.0592 volts over 6, the number of moles, times the log of K. And then if we rearrange our equation, we can solve for K, right? So log K here is equal to 0.71 volts divided by 0.0592 volts over 6, whatever that gives.